Hello everyone. So let's do the review for our what's going to be our last quiz, quiz number 17 on minimum spanning trees. And I'm going to give you a tree, something like this, perhaps, where every edge has a cost, a weight, whatever you call this, and this is clear here. Oh, I forgot to give this a value. Okay, and what you have to do is use either of the two algorithms that we discussed in 11.5. We have either prim algorithm or you can do Kruskal. And Kruskal is simpler in the sense that it has one less restriction. In prim, you're gonna try to find the edge of least cost that is adjacent to what you have already without making a circuit. And in Kruskal, you drop the adjacency and you just keep doing until you do have a tree. And how do you know that you reach a tree? In Kruskal especially, but also in prim, apart from drawing it, you can draw it, but you don't even have to draw it, you're just counting. So you count, so that the first thing perhaps we should do is how many vertices do we have here? So the number of vertices is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the 12 vertices. So that means that I have to come up with 11 edges to no more, no less, and that will give me a tree. Okay, so that's the beautiful part of this. Okay, and so I'll do the prim first. So you might say, okay, why would you even consider the prim algorithm? Because it is more, it's strict, it's more restrictive. Yes, but it has the advantage that it continues to build a tree. So you could think of this as perhaps as follows. Suppose you position for either algorithm you can put wherever you can start wherever you want. So okay, imagine we are here, and this is information that you gather as you go along. Let's say if you're in a vertex, the only thing you can see are the values of the edges that go out. In that case, is that the case? Your prim algorithm will can only be, you cannot use your Kruskal algorithm because you don't know yet that. So let's start this off. Okay, I'm going to start with prim, and then I'll point out to you what it is that makes it different from Kruskal. I do a Kruskal as well later on. Let me make sure. What should I do here? Let me make a copy of this guy first before I do anything else, so that I can do the same tree later again. I'll copy here. Sorry. Copy. Okay. So, well, let's start with picking an edge of lowest value here, 1. So, oh, we have to give names, right? Sorry, that's one thing I forgot to do here. A, B, C, D, E, F, G, H, I, J, and K. Okay? The names are important because we need to list what our edges are. You can draw them, but that's not enough. So I want you to also list them. So I list A, D. You can just write them as this, as the two endpoints. That's uniquely determined, and you write also the cost, 1. So now you have two vertices that are within your vision, let's say, and from these vertices you can see that you have a two edges, another 2 edge, another 2 edge. So you have to pick one of those 2 edges. One of these edges of cost 2. So you pick randomly one, and so there are going to be many different choices you can make here, right? So I'm going to just take that one now. So in this now gives you even more information. You now also know what goes out of E. And there is a 1 edge, a 3 edge, and a 1 edge. So I have to always take the lowest. That is the prim algorithm, the one of lowest cost. So I'm going to take the 1 here. Let's take this 1 here. Okay. And oh, sorry, there's one more I wanted to make here. I forgot to make this one here. I want this also 1. Okay. Sorry, yeah. So I took EF, and its cost is 1. Okay. I have visited F, so I have new things. There is a 2 and a 5. But actually, that 2 edge here is already out, because it will make a circuit. So I can already scratch this out. Will never be able to consider it anymore. So I have now 4 vertices from which I can have information, namely there's a 2 and 2 out. This one is a 3. Sorry, let me write the 3 a little bit higher. Perhaps it's clear that this the 3 stands for this guy here. So that's a 3 here. There's a 1, another 1, and that's it, the new ones. So I need to take one of these ones. Okay, doesn't matter which one I take, so I'm going to take this one. Oh, I wrote it the 1 twice there. Sorry, now I got a little bit. Okay, so that is so EC has value 1. Okay, there are still 1s, so as long as I see 1s, I'm going to take them, right? So out of E, another 1 emerges, and I'm going to take this one, EH. So EH also has value 1. There, what else? There is, what have I left? Look, there is a 1 left here that is to my adjacent, but it makes a circuit. Okay, so whenever you connect the 2 vertices that are already on your path, because what you're creating is on your tree. Sorry, whenever you connect 2 vertices that are already on your tree, you will actually make a circuit. So this is out. Although this is a 1, I cannot take this. So sometimes 1s. Not all the low ones can be taken. Okay, that leaves me. Oh, I see. Oh, okay, I see. I'm sorry. I erased this. There was a 1 that I erased, right? This was the value of this one here. Sorry. On the quiz, I'll make it show much better which is where. I don't know. I was a bit sloppy here, but put in my numbers. Okay. So we have still from out of H emanates this 1 edge. So I can use that. So that is HB. HB, and that's 1, or BH, doesn't matter. Now a couple of others are excluded. For instance, this would make a circuit, so would this one. Okay? It's not necessary to always list all of them, but it helps if you would do that, because then you're not gonna, you're not distracted by them anymore. And I think the BC edge would also create a circuit, right? Yes, right, because it connects, yeah. So all these are out. Right, so no edge that connects to already a vertex on the tree is allowed, okay? So what have we left? Okay, we have to, there are no 1s anymore, I think, at least not at the moment, that I can take. So I'm looking for 2s that I can take. I see here 1. One of them is this one, HI. So HI is 2. That leads me to take this one here, the IJ. Okay. And, there's a 2 that I can take. Let's take it here. This one. Oh, I didn't give this guy a name. So this is, well, let's call this L, I guess. Wait, did I count? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I counted correct. I just didn't name it. Okay. So this was JL, right? JL, and that has value 2. So 2 more. Well, we know that each time I will connect, so for instance, I can never take this one because it connects already 2 that are on the circuit, on the tree, so that must be a circuit somewhere. I don't even have to check. I know that it will create a circuit, so I can get rid of that one. But there are a couple of left that I can take here. So let's see what we have. We still are looking for the lowest possible ones. There are no 1s anymore, but there's still 2s that I can take, and there's this one here, for instance, DG. GG has value 2. Oh, there's actually a 1. Sorry, I didn't even see that one here. Yeah, right, there is one, and I will take it because here it is, GK. And that's 1. And that's it, right? Because I have reached the number of required edges, so this is a tree, and indeed you see every vertex is lying on exactly 1 edge. No, not on exactly 1 edge, lies on an edge, lies in the tree, sorry, that's what I say. So this is a spanning tree of your graph, and what is its cost? Well, 3, 4, 5, 6, 7, 8, 9, 10, 14, 15. Okay, So that's how this works. It's very simple. You have to be very careful and follow the instructions, but there are many different answers. So it's not so easy to, well, to compare your answer with the solution that I will post. In principle, if you get a 3 and you get the same value, you should be okay, right? That should be okay. So let me now do the same, but using Crosscode. But instead of the minimum spanning tree, I do the maximum spanning tree. We discussed it in the homeworks already, and there's nothing different except that instead of looking for the smallest value, look for the highest value. So let's do this. So I'm going to paste my image here. I guess I have to do it this way. Paste image. Okay, why is it so small? Come on, guys, I want you bigger. Here we are. Okay. Right, there were a couple of things. Oh, some things were missing, right? I didn't even. Right, there was one here that I added later. That has value 1, right? I did a couple of redactions, but I think that's it, right? Yeah, so this is 1 and this one is 1, right? That's. Yeah, I don't know. Perhaps. I cannot erase this thing, sorry, I have to not. Okay, so sorry, this cannot be erased. So this one replies to this and this one refers to this one. Okay. And then we had to give names, so let's keep the same names. A, B, C, D, E, F, G, H, I, J, and this was an L because I called this K. All right. So let's do the unknown cross-call and maximal. Okay, so the procedure is the same. There's still the same number of vertices, so I need 11 edges. So this will be my edge, and this will be the cost. Okay, the most expensive one, or the best one, if you want, the most points, say you're playing a game, you want to get as many points as possible, is the 6, the down here. So this 6 here, so we take this one. So you see, another disadvantage of Crosscall is you cannot just start anywhere where you want, because you have to take one of the highest values. If there are several ones, you still have a choice, but if there's only one, you have to start there. Where in Prim, we could decide ourselves where we started. Well, that's not entirely true either. No, that is true. Yes, no, sorry, it's not entirely true because you also had to start from one of the lowest values. I'm sorry, yes, no. What I said applies equally to both. So sorry, it is not forget what I said before about advantage of Prim. But the advantage of Prim is that there's these games, I forget now what they're called, that where you start building. You're building up a village and you discover more and more of what's around you, and it's only when you visit a square you see what the next squares are. And this is basically what happens, right? When you visit a vertex, you can see what are the costs of going out. That is why Prim algorithm has an advantage over Crosscall. But Crosscall has an advantage that it is somehow quicker because you just pick the highest values that you can find. So I pick 6, and now I see there are 5 left, so I take this 5 here. So that is, I didn't write down my K. So KJ was 6, and then FK was 5, and then there's another 5 that I have to pick, is 5, and that is CJ. So for some reason, in this case, we still have a tree, but normally when we do this, you get disconnected things. So we now pick, the next value that is available is 4, so BC. So BC is 4. Then what else? There are trees that I can take. Okay, let's take this tree. No, where is the tree? What is this little tree doing down here? I never used that, right? Sorry, I don't know what this is. I don't know this is. That's not meant. The tree is this one here. This is this one. So it is BE. And then the rest are all 2s or 1s. So let's start taking values 2. So here's one value 2. So let's take one that is finally not connected to what I have so far. GI, that is 2. I can take another 2 here. HI. there's a 2 I see here. I'm going to take this 2, AB. Okay, so there's another 2 here, AB. Now, another difference, perhaps what makes cross-call in sense a little bit less easy to work with, is in Prim, when you know that you can never draw an edge between vertices that have been already visited, because that will create a circuit. That is not true in cross-call, because you're not drawing one single tree, you're drawing several trees. In this case, we have this huge tree outside here, and this is a small tree inside. So if you connect, if an edge, for instance, that would connect one tree with the other tree will not create a circuit. This will not create a circuit because I'm connecting two disconnected trees. However, this edge will. So you have to analyze a little bit better whether an edge is actually creating a circuit or not. So this edge creates a circuit, so I can already erase that. There are more 2s to take. Here I see a 2 here. I'm going to take this 2. Here, this one is DG. Another 2, okay, I have another 2. Oh, we have to think, because we are connecting 2 vertices, but this is a single tree, and this is another tree, so I can connect this. They will not make a circuit yet. So, okay, so that is DF. And one more I need, so where is it? Oh, I have one more 2 left here, and that is JL. By the way, that's the only other one I could take. Everything else is now ruled out, because everything else has been visited, and it's before, so here at this stage already, before I did the last one, so we had a tree, okay, and everything was already on it except L, so there's none of the remaining edges I could use except for the JL edges. So it was really the only one I could use, and that was luckily value 2. So JL has value 2. So what's the maximum here is 16, 20, 23, 25, 27, 29, 31, 33, 35. Okay, so that's a maximum tree and using. So I've done both methods. I might ask you to use a particular method, or I might say you choose yourself. Okay, all right.